Hello, everyone. So last week we have completed our discussion on virtual memory, and particularly virtual memory paging, with focus on the two-level page tables, or actually the multi-level page tables and their usage, followed by the invertible page table and the translation look-aside buffer, and how the address translation is conducted over each data structure used in virtual paging schemes. And we have also discussed different memory management across various operating systems, including Linux, Unix, Android, and Windows. And this week in particular, we will focus on the second strategy in memory management, in virtual memory in particular, which is virtual segmentation. And we're going to see a different level of combining paging and segmentation in memory management, which is called combined paging and segmentation. In order to achieve an efficient memory management through the operating system, there are many operating system policies that we should enforce to come up with the best operating system management strategies. So lastly, in today's class, we will also discuss different operating system policies, in particular for virtual memory. Now let's start the first discussion on segmentation. So when it comes to segmentation, we know that segmentation allows the programmer to view memory as consisting of multiple address spaces or segments. Segments could be actually of unequal or even indeed dynamic sizes. Memory references consist of a form of address. This address, as we have clearly said before, it has two portions. The first one is the segment number and the offset. This is the virtual address when we are using just segmentation, virtual segmentation. This organization actually that allows the memory management to view memory as multiple address spaces or even multiple segments. This organization has a number of advantages to the programmer over a non-segmented address space. The first one, it simplifies the handling of growing data structure. If the programmer doesn't know ahead of time how large a particular data structure will become, it is necessarily to guess a less dynamic size segment sizes are allowed. It is necessarily to guess such number of segments. With segmented virtual memory, the data structure can be assigned its own segment, and the operating system will expand or shrink the segment as needed. If the segment that doesn't need to be expanded in the main memory, and there is insufficient room, then the operating system may move the segment to a larger area of the main memory, if available, or even swap it out. The enlarged segment would be swapped back in at the next opportunity. The second advantages of using virtual segmentation is that it allows programs to be alerted and recompiled independently. Without actually requiring the entire set of programs to be relinked and reloaded, we can see that virtual segmentation provides a kind of alternation and even recompilation to programs independently. Again, this is accomplished using multiple segments. A third advantages of using virtual segmentation is that it lends itself to sharing among processes, which means that a programmer can place a utility program or even a useful table of data in a segment that can be referenced by other processes. Finally, virtual segmentation lends itself to protection. Because a segment can be constructed to contain a well-defined set of programs or data, the programmer or system administrator can assign access privileges in a convenient fashion. In the following table, we can see a summarization of the different characteristics of paging versus segmentation, whether it is simple paging and simple segmentation or virtual paging and virtual segmentation. As we have previously talked about paging without simple paging without the involvement of virtual memory versus virtual paging with the involvement of virtual memory, now I would like to provide different characteristics among simple segmentation and virtual memory segmentation. So the main characteristic in both memory management strategies is that the main memory is not partitioned. Also, program segments as specified by the programmer to the compiler. That means the decision is made by the programmer, which is not the case in paging. We guarantee that there are no internal fragmentations using the segmentation scheme, whether it is with the involvement or without the involvement or the virtual memory. We might see external fragmentation when we adopt the segmentation scheme. Also, the operating system must maintain a segment table for each process showing the load address as well as the length of each segment. The operating system must maintain a list of 3 holes in the main memory, and the processor will use segment number and the offset to calculate the absolute or the real address. The only differences between the simple segmentation and virtual memory segmentation is that in simple segmentation, all the segments of a process must be in main memory for process to run unless overlays are reused. On the other hand, in virtual memory segmentation, not all segments of a process need to be in the main memory for the process to run. Segments may be read in as needed. In addition, reading a segment into main memory may require writing 1 or more segments out to the second memory or to the disk. Now let's talk about segment organization. In the discussion we have made before regarding simple segmentation, we have indicated that each process has its own segment table, and when all the segments are loaded into the main memory, the segment table for each process is created and loaded into the main memory. Each segment table entry contains the starting address of the corresponding segment in the main memory, as well as the length of the segment. The same device, which is a segment table, is needed when we consider a virtual memory scheme based on segmentation. So we're going to do the same strategy in which we will adopt a segment table, and then we are looking into a segment table entry to provide address translation between a virtual address and an absolute or real address. Again, it is typical to associate a unique segment table with each process. In this case, however, the segment table entries become more complex, as I will share with you in the next slide. Because only some of the segments of a process may be in the main memory, that means a bit is needed in each segment table entry to indicate whether the corresponding segment is present in the main memory or not. If a bit indicates that the segment is in the main memory, then the entry also includes the starting address as well as the length of that segment. In addition to this, another control bit in the segmentation table entry is needed, which is the modified bit. This bit is used to indicate whether the contents of the corresponding segment have been alerted since the segment was last loaded into the main memory. If there has been no change, then it is not necessarily to write the segment out when it comes time to replace the segment in the frame that is currently occupied. Other control bits as well may be also presented. For example, we see protection or sharing bits. The protection and sharing, if they are acquired to be managed at the segment level, then some control bits are added into the segmentation table entry for this purpose. Again, it's typical to associate a unique page table with each process. In this case, however, the page table entries become more complex. Because only some of the pages of a process may be in main memory, a bit is needed in each page table entry to indicate whether the corresponding page is present in the main memory or not. If the bit indicates that the page in the main memory is included, then the entry also indicates the frame number of that page. This is different when we compare it to segmentation only strategy. For segmentation only strategy, we have the present bit, and we also have the modified bit. We have some other control bits. And if the present bit is set to 1, we do have the length of the segment as well as the segment base address. The modified bit is merely added to indicate if the content of this segment have been alerted since this segment was last loaded into main memory or not. So these are the differences between the virtual address for paging only versus virtual address for segmentation only, in which we reserve a couple of bits for the page number and the rest is just for the offset. I'm going to use D for it. For segmentation only, we still reserve a couple of bits for the virtual, for the segmentation number, the segment number, and some other bits for the offset. The segmentation table includes information about the length of each segment, as well as the starting address or the segment base address, in addition to the present, the modified, and other control bit. In the page table entry, which is more simplified version, we only store the direct frame number that in which each page is loaded. So the basic mechanism for reading a word from memory involves the address translation between virtual address into a real address within the main memory, or sometimes we call it a physical address. The virtual address consists of, as we clearly said before, a segment number and an offset. This could be only done if we do have the segmentation table or the segment table. Because the segment table at this point is of variable length, depending on the size of the process, we can't actually expect to hold it in registers. Instead, it must be in main memory to be accessed. In the following figure, we see a hardware implementation of this scheme, similar to what we have discussed when we talked about paging. That means when a particular process is running, a register will hold the starting address of the segment table of that process. The segment number of a virtual address is primarily used to index that table of that process and look up the corresponding main memory address for the start of the segment. This is added to the offset portion of the virtual address to produce the desired real address. Both paging and segmentation have their strengths. For example, in paging, which is transparent to the programmer. So the programmer is not aware about how many pages, the page sizes. It's only all of this information is determined by the operating system. For paging, we know that there is a small chance, or actually it eliminates external fragmentation, and thus it provides efficient use of the main memory. In addition, because the pieces that are moved in and out of the main memory are of fixed equal sizes, it is actually possible to develop a sophisticated memory management algorithm that can explore the behavior of programs, as we will see later when it comes to memory management policies. Segmentation also enjoys some advantages. First, it is visible to the programmer as compared to paging, which is transparent to the programmer. Segmentation has the strengths listed earlier, including the ability to handle growing data structures, modularity, and support for sharing and protection. To combine the advantages of both paging and segmentation, some systems are actually equipped with processor hardware and even operating system software to provide both paging and segmentation. In a combined paging and segmentation system, a user address space at this point is broken up into a number of segments, such that, and of course, this division or this partitioning is at the discretion of the programmer. And then each segment in return is broken up to a number of fixed pages, which are equal in length to a main memory frame. If a segment has length less than that of a page, the segment occupies just one page. From the programmer's point of view, a logical address or the virtual address will still consist of a segment number and a segment offset. However, from the system point of view, the segment offset is now viewed as a page number and a page offset for a page within the specified segment. In the following figure, we can see a structure to support combined paging and segmentation. Associated with each process is a segmentation table and a number of page tables, such that we have one page table per each process segment. When a particular process is running, a register will hold the starting address of the segment table for that process. Presented with a virtual address, the processor uses the segment number portion to index into the process segment table to find the page table for that segment. Then, the page number portion of the virtual address is used to index that page table and look up the corresponding frame number. This is combined with the offset portion from the virtual address to produce the desired real address in the main memory. This is how address translation is conducted in a combined segmentation and paging scheme. Looking to the following figure, we can see that the segment table entry and the page table entry formats are different. Both of them are similar to what we had before, except there is minor changes. As before, what we have seen now is the segment table entry contains the length of the segment as well as the segment base. which now refers to the starting address of the page table. The present and the modified bits are no longer needed in the segment table entry because these matters are now handled at the page level, not at the segment level. We still need some control bits that might be used for purposes like sharing and protection. The page table entry is very essential in the same fashion as we have seen before in pure paging system. Each page number is mapped to a corresponding frame number. If that page is present in the main memory, that means we still need the present bit in the page table entry. And the modified bit is still used such that it is used to indicate whether this page needs to be written back out when the frame is allocated to another page. There may be other control bits that we might add in the page table entry that deals with protection or maybe other aspects of memory management. So in combined paging and segmentation, we do need a segment table, which we index it through the first couple of bits from the virtual address. And we also need a page table, which we will index it through the segment page within the segment table entry. And then once we index the page table, we will extract the frame number, which later will be combined by the offset. To compose our real address. This is how the address translation is conducted in combined paging and segmentation scheme. As we have seen so far, segmentation lends itself to the implementation of protection and sharing policies. And because each segment table entry includes a length as well as a base address, a program cannot actually access a main memory location beyond the limit of the segment, which has to be within the length of the segment. To achieve sharing, it is possible for a segment to be referenced in the segment table for more than one process. The same mechanisms are, of course, available in a paging system. However, in this case, the page structure of a program and data is not visible to the programmer, making the specification of protection and even sharing requirement more awkward. So we can see on the level of protection, segmentation as a memory management scheme lends itself to both protection and sharing policies. In terms of sharing, because for each segment, it has a start address and it has a length, then there is no memory access beyond the limits of the segment. And sharing can be achieved by segment referencing through multiple processes. This is the only criteria if we are allowing sharing at the process level using segmentation. So now let's talk about the design of the memory management portion of an operating system and what exactly it depends on. The design of memory management portion of an operating system actually depends on three fundamental areas of a choice. The first one is whether or not to use virtual memory techniques, whether we need actually to involve a virtual memory management or no, or just deal with the memory immediately. Second, the use of paging or segmentation or even both. That's a decision has to be made. Are we going to use just paging or just segmentation or even combined version? The third one are the algorithms that are employed for various aspects of memory management. At this point, the choice made in the first two areas, I'm going to refer to this area number 1 or area number 2, depends actually on the hardware platform available. As we have seen before, earlier Unix implementation actually did not provide virtual memory because the processors on which the system ran did not support paging or even segmentation. Neither of these techniques is practical without hardware support for address translation and the other basic functions. Um, I would like also to add, in addition to this discussion about the first two areas and how it's hard to adopt this, especially in the early computers, Unix implementation, two additional comments that I would like to also to add about these two are like item number one, item number two in the corresponding three fundamental area of choices. First, with the exception of operating systems, for some of the older personal computers, such as Microsoft DOS and even specialized systems, all important operating systems provide virtual memory. Second, pure segmentation systems are becoming increasingly rare. This is mainly because when segmentation is combined with paging, most of the memory management issues comforting the operating system designer are only in the area of paging. So it might be better to just focus on paging. So in the following few slides, what I will discuss is just concentration on different areas and different scenarios that we could adopt to provide an efficient memory management using operating system software across different memory management policies with focus on paging only. When it comes actually to the third choice over here, which is related to the algorithms that are employed for various aspects of memory management, this is mainly related to the memory management policies employed or adopted by the operating system, which will be discussed in more details in the next few slides. So in the following table, we can see the key design elements that we will examine to provide efficient operating system policy management, especially with the involvement of virtual memory. In each case, the key issue is one of performance characteristics. We would like, for example, if you would like to provide an efficient memory management, what are the optimum or what are the best operating system policy to achieve such an efficient memory management? If we are talking about the performance level, for example, what are the main policies that the operating system must invoke to minimize the rate at which page fault will occur, or to minimize or to maximize the processor utilization? But because we are talking now about the memory management, how efficient our memory management is, so we are mostly referring to a performance related to minimization of the rate at which page faults occur. Because actually page faults cause considerable software overhead. So at the minimum, the overhead includes deciding which resident page or pages to replace, and even the input-output of exchanging pages. Also, the operating system must schedule another process to run during the page input-output, which actually causes a process switch. Accordingly, we would like to arrange matters so that during the time that a process is executing, the probability of referencing a word on a missing page is minimized. So this is another criteria by which we would like to build or to develop an efficient memory management using different operating system policies. So which actual policy is the best? Which policy works the best, or like the optimum policy to guarantee an efficient memory management? My answer to this is there is no definitive policy that actually works the best. As we shall see, the task of memory management and paging, which I will focus on in the next few slides, is very complex. So to guarantee that we have an efficient memory management, like efficient memory management policies, we have to come across different strategies related to fetching. So which fetch policy is the best? Is demand paging the best versus pre-paging, which I'll talk about it next? Or What are the optimum placement policies? When it comes to replacement, page replacement, there are different replacement policies using basic algorithms as optimum replacement policy versus the least recently used policy, the LRU, or the first in, first out policy, or even the clock policy. Which one among all of these algorithms is the best to be used to provide an efficient performance of a memory management protocol, which in our turn, we will judge it based on minimizing the number of page fault? It's not known. So we would have to try each one of these algorithms separately based on the flow of memory access stream, and came up with a recommendation which one of those strategies is the best. Also when it comes to page buffering, we have to know which policy is the best for it. And when we talk about resident set management, which I will address in the next few slides, is fixed resident set size is optimal versus variable resident set size. For replacement scope, is global is the best or local is the best? There is no answer to which strategy is the best, because it's a complex process. So furthermore, finally, if I will continue on this, we need also to address the cleaning policy. Is a demand policy versus the pre-cleaning policy, which one to adopt and when? And of course, to complete the operating system policy for virtual memory management, we need to provide what we call load control, which mainly depends on the degree of multi-programming. Furthermore, the performance of any particular set of policies depends on the main memory size, the relative speed of main and secondary memory, in addition to the size and the number of processes competing for resources, as well as the execution behavior of individual programs. The execution behavior of individual programs actually depends on the nature of the application and the programming language and compiler employed. Also, it depends on the style of the programmer who wrote it. And if we are working on interactive program, we will add to this list the dynamic behavior of the user. So there is no final answer to which policy or combination of policies are the optimum to be used, but we know that for smaller systems, the operating system designer should attempt to choose a set of policies that seems good over a wide range of conditions. Based on the current state of knowledge, this could be easily retrieved. However, for larger systems, particularly like mainframes, the operating system should be equipped with monitoring and control tools that allow the site manager to tune the operating system to get what we call good results. This is mainly based on the site conditions. Now let's talk about the first policy in efficient virtual memory management, which is fetch policy. The fetch policy actually determines when a page should be brought into main memory. The two common alternatives for fetching a page into the main memory is either demand paging or pre-paging. With demand paging, a page is brought into the main memory only when a reference is made to a location on that page. If the other elements of memory management policy are good, the following actually should happen. When a process is first started, there will be a flurry of page faults. That means as more and more pages are brought in, the principle of locality would suggest that more future references will be to pages that have recently been brought in. Thus, after a time, matters should settle down and the number of page faults should drop to a very low level. This is with the inclusion of demand paging. On the other hand, for pre-paging, pages other than the one demanded by a page fold are brought in. Pre-paging, like actually it explores the characteristics of most secondary memory devices, such as disks, which have seek times and even rotational latency. If the pages of a process are stored in a continuous fashion in the secondary memory, then it is more efficient to bring in a number of continuous pages at one a time rather than just bringing them in one at a time over an extended period of time. And this is actual, of course, will allow this policy to be uh, ineffective if most of the extra pages that are brought in are not referenced. The pre-paging policy could be employed either when a process first started up, in which case the programmer would actually somehow have to designate desired pages or every time a page fault occurs. This later point will actually seem preferable because it's invisible to the programmer. That's why we might adopt it. Pre-paging should not be confused with the swapping. When a process is swapped out of memory and put in a suspended state, all of its resident pages are moved out. When the process is resumed, all of the pages that were previously in main memory are now returned to the main memory. As we talked about fetching policy, it is well considered to talk about the placement policy. The placement policy actually determines where in real memory a process piece should reside. If you are talking about in a pure segmentation system, the placement policy is an important design issue because policies such as best fit strategy or even first fit strategy and so on, as we have discussed before, are possible alternatives. However, for a system that uses either pure paging or even paging combined with segmentation, placement is usually irrelevant because the address translation hardware and the main memory access hardware can perform their functions of any page frame combination with equal efficiency. There is one area in which placement does become a concern, and this is the subject of recent research and development. A lot of research is conducted in this area on a so-called non-uniform memory access multiprocessor. Non-uniform memory access multiprocessor, which is the distributed sharing memory of the machine can be referenced by any processor on the machine. But the time for accessing a particular physical location will actually vary with the distance between the processor and the memory module. That means the performance at this point will depend heavily on the extent to which data reside close to the processors that actually uses them. For the NUMA version systems, an automatic placement strategy is desirable to assign pages to the memory module that provides the best performance. In addition to fetching placement, we need to talk about replacement policies. In most operating systems, the treatment of memory management includes a section. This section is called the replacement policy, which actually deals with the selection of a page in the main memory to be replaced when a new page must be brought in. This topic is sometimes difficult to explain because several interrelated concepts are involved, including how many page frames are to be allocated to each active process, or whether the set of pages to be considered for replacement should be limited to those of the process that cause the page fault, or encompass to all the page frames in the main memory, or even another issue related to the question about among the set of pages considered, which particular page should be selected for replacement. We shall actually refer to the first 2 points as the resident set management, which is the concern on how many page frames to be allocated to each active process and whether the set of pages to be considered for replacement should be limited to those of a process that caused the page fault or not. This is more related to resident set management, which will be discussed in the next few slides. But for the replacement policy, it's more or less related to among the set of pages considered, which particular page should be selected for replacement. So the area of replacement policy is probably the most studied area of any area of memory management. When all of the frames in the main memory are occupied, and that means it's necessarily to bring a new page to satisfy a given page fault. The replacement policy determines which page currently in memory is to be replaced. All of the policies have their objective that the page that is removed should be the page least likely to be referenced in the near future. This is main objective of different replacement policies. There is often a high correlation between recent referencing history and near future referencing patterns. Thus, most policies try to predict future behavior on the basis of past behavior. One trade-off that must be considered at this point is that more elaboration and sophistication is needed when we design a replacement policy, which would need a greater overhead either on the hardware or the software to implement or to provide an efficient replacement policy. Regardless of the resident set management strategies, which I just talked about them, which deals with how many page frames are to be allocated to each active process, or whether the set of pages to be considered for replacement should be limited or not to the process that has caused the page fault. There are a couple of algorithms that are used for replacement. The basic algorithms that are used just for replacement, regardless of the resident set management, could be one of four. The first one is the optimal policy replacement, or the least recently used replacement strategy, or strategy or algorithm. The first in, first out replacement algorithm, or the clock policy. If we look to the following example, it shows different outcome for the same page address stream. So given the same page address stream, and the stream is in order, like we have the first frame 2, followed by frame 3, followed by frame number 2, frame number 1, and keep going, we can see that we have different outcomes for the 4 different replacement strategies. This with the assumption that we have fixed frame allocation as well as fixed resident set size. And this process has 3 frames. We can see that for the optimal strategy, we do have 3 page faults, while for the least recently used strategy, we have 4 page faults. For the first in, first out replacement strategy, we have 6 page faults, and for the clock strategy, we have 5 page faults. So here we have 3 page faults for the optimal strategy, 4 page faults for the least recently used, and 6 for the first in, first out, and 5 page faults for the clock strategy. So if our criteria, which replacement policy strategy would you use to provide an efficient memory management on the scale of replacement, which means a criteria to minimize the amount of page faults. At this point, maybe the selection will be the optimum strategy because it has the lowest number of page faults. The question is, how could we define the moment at which a page fault would occur? And what are the main definitions and steps in each of those replacement strategies? Let's discuss each one of those strategies separately. I will start now by the optimal policy. Sometimes we call it the OPT. The optimal policy selects for replacement. So now we need to make a decision about which page to be replaced. For the optimal policy, it selects for replacement. The criteria is it chooses the page for which the time to the next reference is the longest. It can be shown actually that this policy results in a fewer number of page faults, as we have seen before, just 3 of them, which I will explain to you how you could extract those page faults. Clearly, this policy is impossible to implement. And the reason for this, because it would require the operating system to have perfect knowledge of future events. However, it does serve as a standard against which to judge in real-world algorithms. In the following figure, we can see an example of the optimal policy. This example assumes that we have a fixed frame allocation, fixed resident set size for this process, and the process is of 3 frames, and the execution of the process require references to 5 distinct pages from page 1 up to page 5. The page address stream formed by executing the program is 2 followed by 3, 2, 1, 5, 2, 4, 5, 3, 2, 5, 2. Now we need to perform the optimal policy strategies and see how many page faults would occur and the final allocation of pages using such a strategy. Now we know that we have 3 fixed. So initially we started by 3 empty frames. The first frame, the first one, which is page number 2. So page number 2 would be assigned the first frame. So far we don't have a page fault because we still have free location in the memory in which a page can be easily loaded into the main memory. Now we'd like to provide access to page number 3. So now page number 3 can easily be added. So far we still don't have a page fault. And then we reference 2. So reference 2 is in the memory, so that's good, no page fault. Now 1 is a new page, so I will add it to the clear empty location. So far we good. So at this point, I don't have any page faults. Now here we go. We have page number 5. So page number 5 would like to, at this point, we would like to replace one of the pages in the main memory with the incoming page 5. So then we will reference page 5. Page 5 is not in the main memory. So to reference this page, we have to load it in the main memory. So we have to extract one of the pages. We have to replace it with page number 5. But the question is, which page to replace? Is it 2 or 3 or 1? How the optimal strategy works? The optimal strategy, it replaces the page that the time to the next reference to this page is the longest. So if we look to the corresponding set here, we would like to know, are we going to replace 2 or are we going to replace, let me change the color. Are we going to replace 2? Are we going to replace 3 or are we going to replace 1? If we look ahead, this is the future reference. Next, I will replace 2. So the next reference is 2. So no way I'm going to replace 2. And then I will 4, and then 5, and then 3. So the next one would be reference is 2 followed by 3, and I don't see 1. So maybe in future reference, there will be long time taken until I will reference number 1. So maybe I will take page 1 out and then put page 5 instead in the same location as of page 1. So now this where a page fault has been generated. So when 5 has arrived, there is no 5 in the main memory, so a page fault has been created. So the solution is to replace a given page in the fixed size frame. The decision is which page to be replaced. At this point, using the optimal policy, look ahead, see which one has the longest time for the next reference. Now, with arrival of frame page number 2, is it in the main memory? Yes, so we good. So there is no page fault. Now with page number 4, there is no page number 4, so this is second page fault will be generated, and we need to decide which page to be replaced. Is it 2, or is it 3, or is it 5? Again, we have to look ahead for future reference. So the next one to be referenced is number 5. That means 4 will not replace 5, followed by 3. And the longest one to be referenced at this point would be number 2. So 4 would replace 2. So now we have 4 and a 3 and a 2 in this time frame. Now, sorry, 4 and 3 and a 5, because 4 now has replaced 2. Previously, 5 has replaced 1. And now the next flow is page 5, that we need to access page 5. Is it in the main memory? Yes, so we good. Page number 3, it's in the main memory, so good. Now we need to reference page number 2. It's not in the main memory, so a page fault will be generated. And we need to decide, are we replacing 4 or 3 or 5? Again, we need to look ahead to the next one to be replaced. So if you look ahead here, the next one is 5. So I'm not going to replace 5. And then 2 will be replaced. Sorry, 5 is next, and then 2 is the next one. So I need to, so 5 will not be replaced, and I need to know number 2 is coming next. So of course, 4 at this point, 2 will replace number 4 because I don't see 4 coming ahead. At this point, it's tricky because we can see next 2, but we don't see 4 and 3. So which one I replace it? Is it 4 and 3? Maybe the recommendation would be 4 if we have the entire stream. Now we do have at this time frame, we have a 2, a 3, and a 5. The next reference would be in 2, so we good. The next reference would be 2, so we good. So we only have 3 page faults. A page fault occurs when there's a request to access a page, and this page is not in the main memory. So that's where a page fault is generated. And an immediate recovery would be by replacement. So we have to decide which page to replace. Using the optimal policy, that means you need to look in the near future and you choose the page to be replaced. This page should have the longest time with respect to its next reference. If we compare this to the second strategy, which is the least recently used, the LRU. It actually replaces the page in memory that has not been referenced for the longest time. By the principle of locality, this should be the page least likely to be referenced in the near future. As a matter of fact, the least recently used strategy is difficult, doesn't nearly do as compared to the optimal. In some stream of memory access, it may nearly be close to the optimal strategy, but not in all cases. The problem is with this approach, actually, it's difficult to implement. One approach would be to tag each page with the time of its last reference. This would have to be done at each memory reference, both on instruction and data. And even if the hardware could support such a scheme, the overhead would be actually tremendous. Alternatively, one could maintain a stack of page references. Again, this will actually add an expensive perspective. So the two solutions will add a great deal of overhead. So now let's see the outcome. How many page faults will be generated if we decided to use the least recently used strategy using the same page stream. So at this point, the criteria is we need to replace the page that has not been referenced for the longest time. This is the LRU strategy, how the LRU strategy works. So for the same page stream, we start also by 2. 2 is good. We still have free location, so we will add it. We always, for the first 3 frames, we don't have an issue because this is where we say the initialization. Initialization means the first, for a process of 3 frames, we will not have any page faults because we're going to add the first 3 pages immediately into the empty locations. So on 2 and 3 and 2, there is no page faults. Now let's see, when we would like to add the number 1, also number 1 will be added. So that's, let me remove my, my border because that means for the 3, the first 3, we are good. There is no page fault. So up to here, we're still good. Now, when we'd like to access page number 5, this is where a page fault is generated. And the decision is which page to replace. Is it 2 or 3 or 1? We have to look backward at this point and see, not forward, because we're not looking to the near future. It's about the least recently used. So we look backward and we make a decision which one has been used the least. So we can clearly see that 1 was recently used, so I'm not going to replace 1. And 2 has been next. And the longest one that has been used since a long time is number 3. So now 5 will be replacing number 3 because 3 was not used for a long time. Now, when 2 arrives, it's in the main memory, so we don't have a page fault. But when 4 arrives, we will have another page fault because 4 is not in the main memory. But the question is, are we going to replace 2, or we're going to replace 5, or we're going to replace 1? If we look backward, 2 was the most recently used, and 5 is just like before the usage of 2. So the least recently used one at this point will be number 1. So now 4 replaces 1. When 5 arrives, 5 in the main memory, so we're good. And then when 3 arrives, now there is no 3, page 3 in the main memory, so F will be generated, page fault will be generated. And the question is, are we going to replace 3? 3 will replace 2, or replace 5, or replace 4. Again, we have to look backward and see which one is the least recently used before 3 arrives. So 5 was recently used, so I'm not going to remove 5. And 4 was recently used, so I'm not going to remove 3. I will have to remove number 2. So 3 has actually replaced number 2. So this is a bad scenario because now when we remove 2, immediately there is a memory reference to number 2 at which a page fault had just recently occurred. So maybe in some scenarios this strategy performs well, but in this one in particular, I made a decision of removing a page, and immediately there was I didn't look ahead. There is no future reference. So we just look into the past history. So looking to the past history only, I have removed a frame in which the next reference will use such page. Sorry, I have removed the page in which the next reference will access that page. So the amount of page faults would increase. So 2 now would have to replace one of the frames, either 3 or 5 or 4, We look ahead to the least recently used. So 2 will replace number 4 because 4 has not been used in a long time. And then when 5 arrives, we're good. It's in the main memory. 2 arrive, it's good. It's in the main memory. So if you look to this, we have now 4 page faults as compared to the optimum strategies. So far we can say that the optimal strategy is preferable. Now let's move ahead and compare this to the third replacement strategy, which is first in, first out. The first in, first out strategy policy treats the page frames allocated to a process as a circular buffer. And pages are actually moved in a round robin strategy or a style. All that is required is just a pointer that circles through the page frames of the process. This is therefore one of the simplest page replacement policies to implement. The actual logic behind this choice, other than its simplicity, is that one is replacing the page that has been in memory the longest. A page fetched into memory a long time ago may have now been fallen out of use. This reasoning will often be wrong because there will be often some regions of the program or even data that are heavily used throughout the life of the program. So I'm at this point, those pages will be repeatedly paged in and out by the first in, first out. So it might not be at this point a good strategy. So let's see how the first in, first out strategy works for the same page stream. Also, we start by 2. And then keep in mind, it works as a circular buffer, and pages are removed in a round robin style. So again, we don't have page faults until we load the first 3 frames. It just happened here that we have a repetition of access to number 2. So this is where the forced cycle, but that's fine. It depends on the memory access, but at least for the first 3, we are good. If there is a repetition of memory access, we might extend to 4 and 5 or 6 based on if there is a repetition to the same page number or not. Now with the first access to frame number 5, of course, a page fault would occur. And we need to decide, are we gonna replace this? Replace number 5, replace number 2 or 3 and 1 using number with the additional with the incoming page number 5. So if we look to first in, first out of access, this is exactly like the queue structure we talked before in the round robin strategy, where we have pointer pointing to. So this is where 2 started, and then 3, and then 1. And then the remover will depend on the first, or the pointer is pointing to the first arrival. So now 5 is arriving. We know that a page fault has occurred. So the pointer is pointing to number 2. So we know that 5 will replace number 2. So when 5 replaces number 2, so this no 2 anymore, this is 5 over here. So this is where we have our new 5. And the pointer now is pointing to number 3. So the pointer is not pointing here anymore. It's a round robin strategy. So that's our pointer is not pointing to over here anymore, it's just pointing to the next. Now we have a request to access page number 2. Page number 2 is not in the main memory. So another page fault will be generated, and the decision is which page will be replaced. Is it 5, is it 3, or is it 1? We look to the next pointer in our first in, first out. So now 2 will replace number 3. So there is no 3 here, that will be our 2, and the pointer will be pointing to 1. Now with the arrival of frame 4, on page 4, it's not in the main memory, so a third page fault will occur actual. So the third page fault, also we need to decide which one to replace. So now we have to replace the last where the page where the pointer is pointing at, which is number 1. So 4 will replace number 1. So this is no one here. We just have 4. And the pointer in round robin will be pointing back to the first address in our or location in our first in, first out array. So it would be pointing back to the first one. Now with the arrival of 5, 5 is in the main memory, so we're good. But now with the arrival of 3, we don't have 3, we just have 5, 2, 4. So we have to decide, is it 5 or 2 or 4? And of course, a page fault will be triggered. So point to the first pointer, we're going to replace 5. So that means 3 has replaced number 5. So we don't have 5 here, we just have 3, 2, and a 4. Now, memory access 2, that's fine, there is no problem. Now we have another request for page number 5, which we have recently removed. So this is a page fault, of course, but the question is which one to replace. Keep in mind, when we replaced 5 over here, the pointer has moved to the next stage. So now with the request of 5, 5 will replace the next one in our first in, first out circular round robin strategy. Excuse me. 5 will replace number 2. So there is no 2, we have 5, and the pointer is actually now pointing to the third one. And now with the arrival of 2, there is no 2, we just removed it 2 steps backward. So that's where another page fault is triggered, and we need to know which one to replace. Is it 4 or 5 or 3? Where the pointer is pointing, the pointer is pointing now to 4. So now 2 is replacing 4. So as you can see with the first in, first out, although it's simple, it can be easily implemented, but we have 6 page faults. So this is why, although it's simple, you have to be very careful when you implement it, because it might generate a lot of page faults using just the fair strategy of first arrival, first removal. So lastly is the clock policy. The simplest form of clock policy requires the association of additional bit. This bit is associated with each frame, and this bit we refer to it as the use bit. The idea is when a page is first loaded into a memory, into the memory, the use bit for that frame is set to 1. Whenever the page is subsequently referenced after the reference that generate the page fault, its use bit is set to 1. For the page replacement algorithm that uses the clock policy strategy, the set of frames that are candidates for replacement is considered to be a circular buffer with which a pointer is associated. When a page is replaced, the pointer is set to indicate the next frame in the buffer after the one just updated. When it comes time to replace a page, the operating system scans the buffer to find a frame with a use bit set to 0. Each time it encounters a frame with a use bit of 1, it resets that bit to 0 and continue on. If any of the frames in the buffer have a use bit of 0 at the beginning of this process, the first such frame encountered is it chosen for replacement. What happens if all the frames have a use bit of 1? Then the pointer will make one complete cycle through the buffer, setting all the use bits to 0 and stop at its original position, replacing the page in that frame. We can actually see that this policy is somehow similar to first in, first out, except that In the clock policy, any frame with a use bit of 1 is passed over by the algorithm. The policy is referred to as a clock policy because we can visualize the page frames as laid out in a circle. A number of operating systems have employed some variation of this simple clock policy, including the Multics operating systems. Now let's see how the clock policy would work using the same page address stream. Again, keep in mind now we're keeping track with the pointer. So once a page is loaded, we're going to set to 1. Otherwise, when there is all the pages are set to 1, we will we look to where the pointer is looking and then sets everything to 0 and load the page. And that's where the page fault occurs. So now 2 arrives, so 2 is good. I'm going to star means, so my star notion here, it just means the use bit equals to 1. And then the pointer will be shifted to the next one. And then 3 arrives. So 3 will occupy where the pointer is pointing, and then 3 will be easily added to the main memory, and the pointer will be shifted to the third location. Now we have reference access to 2. 2 is in the main memory, so that's no need to load a page in the memory. Now we have a reference access to 1, where the pointer is pointing. The pointer is pointing to the third spot over here. So this is where 1 will be added, and also we will assign stars to every of those pages, which means uses. They have been referenced and loaded into the main memory. Now let's see what happened. Keep in mind that the pointer is always advancing wherever you add a page into the main memory. So now with the arrival of page number 5, if there is a reference to page 5 is not in the main memory. So we need to know which one to replace. You can see the pointer is now pointing to 2. So what will happen is 5 will replace 2. We're going to set 5 to 1, and we're going to clear everything underneath it. So now 3 is, use bit of 3 is set to 0, and the use bit of 1 is also set to 0, and we have advanced the pointer. Now with the arrival of number 2, and don't forget the page fault. With the arrival of number 2 is not in the main memory, so of course a page fault will be generated. Which one will be replaced? We have to look back to where the pointer is pointing, and we add number 2, and then move the pointer to the next cell where a use bit is set to 0. So now we have a memory reference to number 4. It's not there, so what we do first, generate a page fault and decide where 4 will reside, looking to where the pointer is adding and where there is a use bit of 0. So this is where 4 is now added, and the pointer is pointing to number to the first location again. Now we have reference to number 5, so we're good. So we don't shift the pointer, but now with the arrival of number 3, 3 will replace 5. And of course, the algorithm will scan the entire list and set every use bit to 0. So the use bit of 2 now is set to 0. The use bit of 4 is set to 0. And the pointer is now advanced to the next cell. Now with the arrival of number 2, we don't have any problem. Don't forget the page fault, because 2 is in the main memory, but we will set its use bit now to 1. And with the arrival of number 5, we don't have 5, so we're going to have a page fault. So when we have a page fault over here, what should we do next is what we will receive next is number 2. So number 2 is in the main memory, so we're good. So how many page faults do we have now? We have 5 page faults. So if we compare all the strategies now, we can see that the optimal strategy has only 3 page faults. So at this point, we might say that the optimal strategy is the best option to guarantee that we have a minimum number of page faults as compared to the other strategies, including first in, first out, the clock policy strategy, and even the least recently used strategy. All right. So far, we talked about placement policy, we talked about fetching policy, and even talked about the replacement policy. And we have introduced four different algorithms that are widely used to provide efficient replacement strategies. Now, with Page's virtual memory, it is not necessarily, and indeed may not be possible, to bring all of the pages of a process into main memory to prepare it for execution. That means the operating system must decide how many pages to bring in, that is, how much main memory to allocate to a particular process. This is a big question. Several factors actually come into play. The first one is the smaller the amount allocated to a process, the more processes that can reside in main memory at one time. This increases the probability that the operating system will find at least one ready process at any given time, and hence reduces the time lost due to swapping. Another factor, if a relatively small number of pages of a process are in main memory, then despite the principle of locality, the rate of page faults will be rather high. Beyond a certain actual size, additional allocation of main memory to a particular process will have no noticeable effect on the page fault rate for that process. This is mainly due to the principle of locality. So these factors are actual important to consider when we request the operating system to decide how many pages to bring into the main memory. This is one definition to the residence set. So the residence set is considered as the number of pages to bring into the main memory. And to answer this question, we need to provide an efficient management to the resident set. With these factors in place, two sorts of policies are to be found in operating systems. The first one is the fixed allocation policy, and the second one is the variable allocation policy. In a fixed allocation policy, we assume that a process would have a fixed number of frames in the main memory within which to execute. That number is decided at initial load time, which is at which the process is created, and may be determined based on the type of processes. A process could be interactive process, it could be a batch process, or it could be related to the type of the application. So, or maybe actual based on some guidance from the programmer or even the system manager. With the strategy of using fixed allocation policy, whenever a page fault occurs in the execution of a process, one of the pages of that process must be replaced by the needed page. On the other hand, for the variable allocation policy, it allows the number of page frames allocated to a process to be varied over the lifetime of the process. Ideally, a process that is suffering of high levels of page faults, indicating that the principle of locality only holds in a weak form for that process. This would be given additional page frames to reduce the page fault rate. And as a matter of fact, this will cause the process to have an exceptionally low page fault rates. That indicates that this process is quite well behaved from a locality point of view. And this process will be given a reduced allocation with the hope that this will not increase the page fault rate. The use of variable allocation policy relates to the concept of replacement scope, as will be explained in the next few slides. The variable allocation policy appear to be the more powerful one. However, the difficulty with this approach is that it requires the operating system to access the behavior of active processes. This requires software overhead in the operating system, and is dependent on hardware mechanisms provided by the processor platform. So as we talked about the residence set and whether a fixed allocation or variable allocation would be an option, let's now talk about the replacement scope. The scope of a replacement strategy can be categorized as either local or global. Both types of policies are activated by a page fault when there are no free page frames. A local replacement policy it chooses only among the resident pages of the process that generated the page fault in selecting a page to replace. On the other hand, a global replacement policy considers all unlocked pages in main memory as candidates for replacement, regardless of which process owns a particular page. While it happens that local policies are easier to analyze, there is no convincing evidence that they perform better than global policy. So they might be easier, but in terms of performance, maybe the global replacement scope maybe in some operating systems might be attractive. So the only reason sometimes we use local is because it's simple and it might need some minimum overhead, but not guarantee that they perform well as compared to the global replacement scope. Now, there's a correlation between replacement scope and the resident set size. A fixed resident set implies a local replacement policy, which means to hold the size of a resident set fixed, a page that is removed from the main memory must be replaced by another page from the same process. On the other hand, a variable allocation policy can clearly employ a global solution using a global replacement policy. The replacement of a page from one process in the main memory with that of another process causes the allocation of one process to grow by one page and that of the other to shrink by one page. We shall also see that variable allocation and local replacement is valid combination. And we shall examine these three combinations next in the following chapter. So in this chapter, we will only talk about these combinations, but in the following chapters after today's class, we will talk about these combinations using fixed allocation, local replacement, variable allocation, local replacement, and variable allocation, global replacement. In fixed allocation, local replacement, we have the assumption that number of frames allocated to a process should be fixed. Page to be replaced is chosen from among the frames allocated to that process only. And if we assume fixed allocation global replacement, this is not possible at all. But for variable allocation, we could have either local replacement or global replacement. For variable allocation and local replacement, the number of frames allocated to a process may be changed from time to time. And actually, this is mainly to maintain the working set of the process. And pages to be replaced is chosen from among the frames allocated to this process as well, because that's local. While we are talking about global replacement line right now and variable allocation, now pages to be replaced is chosen from all available frames in main memory. And this causes the size of the resident set to vary, as we have seen before. So an algorithm that follows this strategy is the page fault frequency, the PFF. This algorithm requires a used bit to be associated with each page in memory. The bit is set to 1 when that page is accessed. When a page fault occurs, the operating system actually notes the virtual time since the last page fault for that process. This could be done by maintaining a counter of page references, but at this point, don't forget that you might need a threshold to be defined, and if the amount of time since the last page fault is less than this threshold, then a page is added to the resident set of the process. Otherwise, you just discard all the pages with the use bit of 0 and shrink the resident set accordingly. At the same time, reset the use bit on the remaining pages of the process to 0. This strategy can be refined by using two thresholds, not only one threshold. The first one could be an upper bound threshold, and the second one could be a lower bound threshold. The upper bound threshold is used to trigger a growth in the resident set size, and the lower bound threshold is used to trigger a contradiction, or more or less a contradiction to shrink the resident set size. The time between page faults is related to the page fault rate, although it would seem to be better to maintain a running average of the page fault rate. The use of single time measurement is a reasonable compromise that allows decisions about the resident set size to be actually passed to the page fault rate. If such a strategy is supplemented with page buffering, the resulting performance should be quite good. However, using the page fault frequency that would determine the page fault rates, there is a major flaw in this page fault frequency approach, which is that it does not perform well during the transient period when there is a shift to a new locality. That means with the page fault frequency, no page ever drops out of the resident set before the threshold is defined. Since this is not recommended, so the page fault traditional algorithm to determine the frequency of page faults doesn't perform well during either the transient time or even sometimes the steady state time. We can see that in addition to the policies we have provided before, it is mandatory to look into the page fault frequency, and monitoring this will help in identifying the page fault rate. Now, let's talk about another policy in our operating system virtual memory, which is the cleaning policy. A cleaning policy is merely the opposite of a fetch policy. A cleaning policy concerned with determining when a modified page should be written out to the second memory. Two common alternatives are considered. The first one is the demand cleaning versus the pre-cleaning. With demand cleaning, a page is written out to the secondary memory only when it has been selected for replacement. A pre-cleaning strategy writes the modified pages before their page frames are needed so that pages can be written out in patches. Both demand cleaning as well as the pre-cleaning have drawbacks. For pre-cleaning, a page is written out but remains in main memory until the page replacement algorithm dictates that it has to be removed. For pre-cleaning, we know that it also allows the writing of pages in patches, but it makes little sense to write out hundreds or thousands of pages only to find that the majority of them have been modified again before they are replaced. On the other hand, the transfer capacity of secondary memory is limited and should not be wasted with unnecessarily cleaning operations that might happen with demand cleaning. Load control, which is another policy that we should consider when it comes to efficient memory management, operating system memory management. Load control is concerned with determining the number of processes that will reside in the main memory. This is not about how many pages we'll bring in. It's all about the number of processes that will reside in the main memory, which has been referred to as the multi-programming level. The load control policy is critical in effective memory management. If too few processes are resident at any one time, then there will be many occasions when all processes are blocked and much time will be spent in swapping. This is one of the things we should consider when we provide a control to the load. On the other hand, if too many processes are resident, then on average, the size of the resident set of each process will be inadequate and frequent folding will occur. This result in thrashing. In addition to control the load, we need also to talk about process suspension. If the degree of multiprogramming is to be reduced, one or more of the currently resident processes must be suspended or swapped out. This would actually be seen across 6 different possibilities with this procedure. The first one is the lowest priority process to be swapped out. And the question is when we decide on removing the lowest priority process, this implements a scheduling policy decision and is unrelated to performance issues. We only relate this to a process with the least priority. So we are not considering any performance issue at this point. Also in memory management, there is a big decision about which process to be suspended. As I have addressed, we talked about the lowest priority process. We might even remove or swap the faulting process. The reasoning is that there is a greater probability that the faulting task doesn't have its working set resident and performance would suffer least by suspending this process. In addition, this choice has an immediate payoff because it blocks a process that is about to be blocked anyways, and it eliminates the overhead of a page replacement and even input-output operation. So, in addition to the lowest priority process or the faulting process, we can also remove the last process activated. What is the last process activated? This is the process least likely to have its working set resident. And I might be an option in some performance monitoring is to remove the process with the last likely to have its working set resident. In addition to the first 3 options, we might even remove the process with the smallest resident set. So this will require the least future effort to reload. However, it penalizes programs with strong locality. In addition, we may even consider larger processes to be swapped out. This obtains the most free frames in an overcommitted memory, making additional deactivations unlikely soon. Finally, we could also consider a process with largest remaining execution window. In most process scheduling schemes, a process may only run for a certain quantum of time before being interrupted and placed at the end of the ready queue. This actually approximates a shortest processing time, which might be considered as related to the first scheduling discipline related to the size of the process. How would you consider this as an efficient strategy? There is no answer for it. So it may be one possible action to suspend or to swap out a process just because it has the largest remaining execution window. So as we have discussed today, we were able to cover materials related to segmentation, virtual segmentation, combined paging and segmentation, address translation, how address translation is conducted when we have a combined paging segmentation strategy. And then we talked about different efficient operating system policies that guarantee at the end we have a framework of management, of memory management that guarantee, at least in terms of performance, we are trying to minimize the amount of page faults. So in summarization, we covered segmentation, combined batching and segmentation across address translation, and how protection and sharing is conducted using segmentation or combined batching and segmentation. We also talked about operating system software and its policy to provide efficient memory management, starting from the fetch policy, the placement policy, different placement algorithms like the optimum policy, the least recently used policy, the first in, first out, and the clock policy. And we also talked about the resident set management in terms of um, the fixed sizes or dynamic sizes, like fixed allocation or variable allocation within a global, local scope or a global scope. And we talked about the page fault frequency and how frequent this could happen. Monitoring the page faults is mandatory in providing an overall efficient memory management. And we talked about different policies for cleaning. Either we're going to use a demand cleaning, in which a page is written out to the secondary memory only when it has been selected for the replacement, or we just allow the writing of pages in patches as we have seen in the pre-cleaning. And we finally talked about the load control in addition to the process suspension possibilities, including removing the lowest priority process, the faulting process, the last process activated, process with the smallest resident set, even we might consider larger processes or processes with the largest remaining execution windows. So this ends this week lecture, and thanks for listening. I'll talk to you next week.